Hi y'all, welcome to section 6.2a. Today we'll be looking at taking the integral of the reciprocal function and knowing what the rule will be. So hopefully you guys remember how to fill in this table. So remember that you have sine and the cofunction over here, cosine. This guy is tangent, and over here is the cotangent. And this guy is secant, and over here we have cosecant. Okay. We're talking about the derivative of the trig functions. For the derivative of sine, so y prime is cosine. The derivative of cosine is negative sine. Okay. The derivative of tangent is the thing below it squared, so secant squared. Okay. The derivative of cotangent is negative the thing below it squared, so cosecant squared. Okay. The derivative of secant is itself times the thing above it. So y prime would be secant of x times tangent of x. And similarly, the derivative of cosecant is itself times the thing above it, except negative. So right here is y prime times negative cosecant of x, cotangent of x. So I know it's been a while since we filled out one of those tables. Hopefully you still have that in your brain. The other rule we need to remember for this section is just what the derivative is if you're taking the natural log of something. So if y equals the natural log of x, then the derivative will be 1 over whatever the argument is, 1 over x. Okay. So chapter 6 is basically just more rules of antidifferentiation or integrals. And so we're going to be looking at what the integral of the reciprocal function is. So if I have something like this, 1 over x. Okay. So let's think about that. If I was just to look at this problem without giving you any heads up on what we should do, hopefully you'd be thinking about rewriting this using an exponent. So 1 over x is equivalent to x to the negative first power. Okay. So x to the negative first. So anytime you have an exponent, we normally use backwards power rule, right? We say, all right, I'm going to add add 1 to the exponent, and then get rid of that by putting the reciprocal out in front. The problem is here, if I add 1 to negative 1, I'm left with x to the 0th, and then I'd really be putting like 1 over 0 out in front, and then plus c. Okay. Obviously that is not going to work. X to the 0th would be 1, and we'd be multiplying by an undefined value. Okay, so that's why this needs its own special rule. This is not, we're not going to be using power rule backwards. So not power rule backwards. Okay, it needs its own rule. Okay, so what we're going to use is the fact that remember that if you take the derivative of natural log, you get 1 over x. So working backwards, if you already have 1 over x, if you take the antiderivative, we will end up with the natural log of x. Okay? So if you have this reciprocal form, essentially you have something to the first power downstairs. Okay? You need to remember that you will get the natural log of x. Okay? Of course, plus c. But there is one little thing that you have to remember about natural log. Okay? I don't know if I have some space where I can sketch. Hopefully you guys remember that the natural log of x, if you graph that, looks like this. Okay? So the natural log of x has a domain of just positive values. So it has to be, x has to be larger than 0. Okay? In order to ensure that the natural log of x will actually work when we say we're going to take the antiderivative of this, we just need to make sure that we keep x positive, and so we throw absolute values around the argument. Okay? So if I'm taking the integral of 1 over x dx, then the antiderivative is the natural log of the absolute value of x. And then of course plus c anytime you have the indefinite integral. Okay, so that is the rule, and we're applying that rule to these problems here. Okay, so if I have the integral of 2 over x dx, okay, all of our other rules still apply. I have a constant up top, or a coefficient, so I can pull that out in front. So this is just 2 times the integral of 1 over x dx. Okay, and the integral of 1 over x dx, that is what we're practicing today. That you need to recognize that it's x to the first power downstairs, so you're saying, oh, 1 over x, that will be the natural log of the absolute value of x. Of course, plus c, and we have that 2 out in front, so you just throw the 2 out in front. So 2 times the natural log of absolute value of x, plus c. If you guys want to stop and try example 2, go for it. Okay. The only difference here is that this is the integral of 1 over 5x, so you have to see that there's really a 1/5 out in front. So this is 1/5 times the integral of 1 over x dx. So again, this piece over here, the integral of 1 over x, that is the natural log of the absolute value of x. 1/5 out in front, don't forget plus c. Okay. So if you have just just a monomial down there, you can just pull out the monomial or the coefficient part in front of the integral symbol. Okay? So example number 3, we start to step it up a notch, and you're staring at this integral, and we want to know what the answer should be. Okay? Some of you, I'm sure when you see example number 3, you see sine over cosine, and you're thinking, ooh, tangent. Okay? But just realize that since tangent is not the answer, all by itself of a derivative of anything, then the integral of tangent is not going to be anything that we already know off the top of our heads. Okay? So this is not any easier to say the integral of tangent. Okay. And in fact, if you were given the integral of tangent, this would need to be your first step, is to rewrite it as sine over cosine, and then we're going to go from here. Okay? So I know this has been a while, y'all, but we're going to be working with u substitutions again. Okay? Again, some of you may be able to do this without a u substitution. You just see it. Totally fine. Okay? But for most of you, I'd suggest that you write out the u substitution. Okay? Because we're studying, in this section, we're studying this whole reciprocal form, where we have 1 over x, or something to the first power downstairs. That will be your kind of strategy tonight, is to try to let u equal whatever is sitting in your denominator, and see if we can rewrite the problem all in terms of u. Okay? So for this problem, I'm going to let u equal my denominator, which is cosine of x. Okay, I know it's been a while. For u substitutions, whatever you let u equal, your next step, you should take the derivative of u with respect to x. So the du dx would equal the derivative of cosine, I know is negative sine of x. Okay. And then always I'm going to multiply both sides by dx. So I get du equals negative sine of x times dx. Okay. Now for a u substitution, I'm going to look back at my problem and rewrite the problem all in terms of u. Okay. So cosine of x was downstairs, and that's what I let u equal. So I have the integral of a u downstairs. Okay. Upstairs I have sine of x times dx. So that's right here, sine of x times dx. I have a negative 1 out in front, so if I divide by negative 1 on both sides, I would have negative du equals the sine of x dx. Okay. So sine of x dx right here, I'm going to replace with negative du. So all of that gets replaced with negative du. Okay. If there's nothing up top, there's really a 1, right? So let's go ahead and pull out our coefficient, which is just really a negative 1. So I have negative 1 out in front, the integral of 1 over u du. So now I've been able to rewrite this problem all in terms of u, so now I can integrate. And I'm noticing that I have a u to the first power downstairs, so this is indeed in that reciprocal form. So I know that the integral of 1 over u would be the natural log of the absolute value of u. The negative 1 will stay out in front, so it's still negative 1. Okay. We have a plus c, but remember we have to plug in what we let u equal back into our original problem. So if we plug our cosine of x back in here, I have negative times the natural log of the cosine of x plus c. Now, there may be various answers on a problem like this. Realize with natural logs, sometimes they'll use logarithmic powers to rewrite the problem. So I don't know if you guys remember this, but if you have a negative out in front, you can actually bring that back as an exponent for your argument. Okay. So if you didn't see this answer sitting here, realize that that negative really could be brought with the cosine for the exponent. So this could really be thought of as a natural log, the cosine of x, quantity to the negative first. And hopefully remember that the reciprocal of cosine is secant. So we could have the natural log of the absolute value of secant of x plus c. I don't think the AP test really does that to you, but in your textbook, if you're looking in the back of the book, if that answer wasn't sitting there, maybe they have that one there. Okay, but I'm sure that would be enough for the AP test. Okay, definitely on the free response. Example number 4, again, you look at this problem, you're integrating x plus 1 over x squared plus 2x with respect to x. You can try a whole bunch of different tools. In this case, if you try to just integrate, you have a quotient, something divided by something. So you're hoping that if you let u equal one part of this, that the derivative of u will already be sitting in the problem, so you can rewrite the whole entire problem in terms of u. Again, for tonight, my suggestion would be try to let the denominator equal u. So if I let u equal x squared plus 2x, take the derivative of that, so du dx will equal 2x plus 2. And then I'm going to multiply both sides by dx. So I get du equals, and I see this 2 is in common in both of those, so I'm going to go ahead and factor out that 2. 2 times x plus 1, and then times dx. Then I'll look back at my problem and see if I can rewrite this problem all in terms of u. So this is what u was. So I have so far the integral of u downstairs. And then I have x plus 1 times dx. So I want to replace x times 1 dx. Okay. If in my work over here I didn't have an x plus 1 and a dx, I would not be able to solve this problem. But I do. I have an x plus 1 dx. So if I isolate x plus 1 times dx, if I solve for that, I end up with dividing both sides by 2, so I have a 1/2 du. This is like the side work. Okay, so x plus 1 dx equals 1/2 du, so that's what I'm going to replace right here, 1/2 du. Okay. Again, if there's nothing up top, there was really a 1 there. So rewriting this problem, I'm going to pull out any coefficient. I have a 1/2 times the integral of 1 over u du. So from here, you're going to use our new rule that says if I'm integrating a reciprocal function, or u to the first downstairs, it will just be the natural log of the absolute value of whatever u is, the 1/2 out in front. Don't forget your plus c, and then plug your u back in. So our u was x squared plus 2x. So I'm left with 1/2 times the natural log of x squared plus 2x, absolute value, plus c. Hope this is making sense, y'all. Let's go ahead and try example 5 and 6. If you're feeling comfortable, you can totally try this on your own. We have the integral of secant squared over 1 plus tangent of x dx. Okay. Try to integrate. Not going to be able to do much all on its own. And so we're going to go ahead and let u equal our denominator. 1 plus tangent of x. Take the derivative of u with respect to x, du dx. And in this case, the derivative of 1 is 0. The derivative of tangent of x, again, if you have your table, you can go back and look. The derivative of tangent is secant squared. Okay, so the derivative of tangent should be just secant squared. And then you multiply both sides by dx. So you get du equals secant squared dx. Now you're trying to rewrite this problem all in terms of u. This right here was a u. So far I have the integral of something over u. And then secant squared dx was sitting up here. So I need to figure out what secant squared dx equals. Secant squared of x literally just equals du. So all this problem is the integral of 1 over u du. So this problem is the exact form of the reciprocal function. So the integral of 1 over u is just the natural log of the absolute value of u plus c, plug your u back in. So the natural log of 1 plus tangent of x, absolute value, plus c. Okay. Now I haven't reminded you of this, but remember at any point, if you're taking an indefinite integral, you can check your answer by taking the derivative of your answer, and you should get back to where you started. Okay. Now realize the absolute value will not show up in your answer. If you took the derivative natural log of this stuff, we'd have 1 over that stuff, times the derivative of that stuff. Okay, and you should end up with the exact integrand. Okay. You should really try this one, y'all. See if you can get it right. So pause, try example number 6. So I'm going to let u equal my denominator, 10 minus x to the 4th. Okay. I go to take the derivative, du dx. The derivative of 10 is 0. The derivative of negative x to the 4th would be negative 4x cubed. Multiply both sides by dx. So du equals negative 4x cubed times dx. And I come back over here and I'm trying to rewrite this problem all in terms of u. So that was my u. So I have the integral of u downstairs. And then x cubed dx is what I need to isolate over here. So x cubed dx, if I isolated that, I would have divided both sides by negative 4. So x cubed dx really equals negative 1/4 du. Okay. So I'm going to replace right here x cubed dx equals negative 1/4 du. And then I'm going to pull out any constants out in front. So negative 1/4 times the integral of 1 over u du. So you guys notice that every single problem so far has only been off by a constant, and that's the whole idea, otherwise we wouldn't be able to integrate. Okay, the integral of 1 over u is the natural log of the absolute value of u, plus c, plug your u back in. So negative 1/4 natural log of the absolute value of 10 minus x to the 4th. And don't forget your plus c. Okay. Now, some of you may have been able to do these last few without a u substitution. Okay, these last two problems, because they are definite integrals, okay, actually require that you do a u substitution. Okay, so you do not have the luxury of not doing a u substitution. Now, the way this is worded, it's not necessarily like you had to do u substitution, but you'll see I'll be giving you some AP problems where they will force you to do a u substitution. They'll say something like, let u equal something, and then they have the setup for the multiple choice. Now, in this particular problem, it's just x, so we won't have to do a u substitution. But on example number 8, we'll show you how AP style will go with that. Okay. So if you have a definite integral, you do this problem exactly like it was an indefinite integral. First, the integral of 1 over x dx would be the natural log of the absolute value of x, and then plus c. Right? If you have a definite integral, though, you do the indefinite integral, so you say, okay, the natural log of the absolute value of x. Instead of writing the plus c, remember you say evaluated from the bottom to the top. Okay. Now, I feel like I changed the numbers, and I did, yes. So I did change this to 1, so didn't have that messy decimal. And so I was just evaluating from 1 to 10. So I'm going to plug in the 10, natural log of the absolute value of 10, minus plugging in the 1, natural log of 1. Okay. And, you know, that's perfectly fine if it was free response. You could totally leave your answer that way. Okay. But if you have actual numbers in here, the absolute value of 10 is just 10. So that's the natural log of 10. Minus natural log of 1 is just natural log of 1. Okay. And natural log of 1, I am hoping that you guys remember that the natural log of 1, if you plug in 1, you get 0. So that guy zeroes out, so you're literally just left with the natural log of 10. Okay. You could have also gotten that answer by remembering if you subtract two logarithms, you can rewrite it as the natural log of the top number divided by the bottom number. So 10 divided by 1, which would also be 10. So no matter what you slice it, you should get the natural log of 10. Okay. And then example number 8, last but not least, classic u substitution problem where they might have the answers in the multiple choice region, or the multiple choice section, given as just the setup, not the actual final answer. Okay. So if this was AP style, they would say let u equal, they would force you to let u equal 2 plus x to the 2/3. And they're going to ask you which setup is equivalent to this setup. Okay. So the first thing you should notice is that if u equals that bottom stuff, then I know in my answer I'm going to have a u downstairs. Okay. And this is the special trick with these. Remember, if we're going from 1 to 8 on your integral, those 1 and 8 values were x values. Okay. If I go to rewrite this whole problem in terms of u, so this is going to be a du back here, I know that these values right here will have to be u values, no longer x values. Okay. So I know that my values are going to change. It's not going to stay from 1 to 8. Okay. The way you get those to change is to plug these values into this expression. If this was x equals 1 to x equals 8, if I plug in x equals 1 right here, I can figure out what u must be. So if u is always equal to 2 plus whatever x is to the 2/3, then if x is 1, 1 to the 2/3 is 1, so 1 plus 2 would give you 3. And if u will equal 2 plus 8 to the 2/3, and I know I've been working with a lot of you on this individually, make sure you know which one's the power, which one's the root, and remember that it's the order of operations does not matter. So I'm going to take the cube root of 8 first and get 2. 2 squared, which is 4, and then 4 plus 2, which would be 6. Okay. So these are my new limits of integration. If I'm going to rewrite this problem in terms of u, I would be saying that I'd be integrating from 3 to 6. Okay. Now I still haven't set up the rest of the problem. I still have to actually do the u substitution and everything in here, and do my u equals. But this will be a major part of, oops, I should have done this work over here. This will be a major part of these problems, is to make sure you remember that the limits of integration will need to change. Okay, so that was, these were x values. If you're going to rewrite it with a u, these have to be new u values. Okay. So if we let u equal that denominator, we're going to go ahead and take the derivative of that, so du dx. By the way, you could have totally gone straight into this. You didn't have to do that first. You can do that later. So du dx would equal the derivative of 2 would be 0. The derivative of x to the 2/3, you pop the 2/3 out in front and decrease the exponent by 1. So 2/3 minus 1 will give us a negative 1/3. Okay. Multiply both sides by dx. So you get that du would equal 2/3 times x to the negative 1/3 dx. Okay. And again here, I'm trying to rewrite this problem all in terms of u. So if I just come over here for a second, if it was just the indefinite integral, I have my u downstairs, and then I have this x to the negative 1/3 dx. So here's my x to the negative 1/3 dx. Okay, so if I want to isolate that, x to the negative 1/3 dx, I must have multiplied both sides by 3/2. So 3/2 du is what x to the negative 1/3 dx equals. So I'm going to replace all of that with 3/2 du. So 3/2 du. And it was integrating. Okay. So if it was an indefinite integral, it would look something along those lines. So I'd have 3/2 times the integral of 1 over u du. But since it's a definite integral, I'll do the exact same thing. So I'll have the 3/2 out in front, 1 over u du. But my limits of integration now will be switched from 1 to 8, from 3 to 6. Okay. So we will do several more of these types of problems where you actually see the multiple choice answers, so you can see what I'm talking about on this. Okay. On a problem like this, you can go ahead and actually anti-differentiate and solve it as well. But if you have a definite integral, I want you to really practice letting u equal your denominator, and then replacing the original limits of integration with your new u values for the limits of integration. Okay. I think that was all I had, right? So good luck, y'all. Hope this made sense.